So it's time to see some of these weak acid calculations in action. So let's go right into a sample problem. Now these will line up with your in-class problems, so you might want to follow along. So we're going to have a generic monoprotic acid, HA, with an initial concentration of 0.12 molar. And what we're told is that it's 5% dissociated. In other words, 5% of its concentration is going to go forward to making products. And we're asked to calculate the Ka. Now remember, in equilibrium problems, we have to be given one of two things. We either have to be told the change to the initial concentration, or we have to be given the Ka value. So if they're asking for the K value, they must have outlined what that change is. And in this case, it's that 5% dissociation. It's going to end up being 5% of the 0.12 molar. We begin by writing out an equation. And remember that if this is any acid, we need to make sure that water is included as part of the reactants. So what's on the screen right now, although it's bare bones, is not accurate yet. So we're going to change the equation to include water to form hydronium, and of course our anion will also be made. And I want to set up a world according to Donovan style problem, a chart problem. We're going to layer in our initial information, our 0.12 molar for my generic acid, zeros for my hydronium and my anion. And again, they did tell us what the change to the concentration was. They said 5% of 12 or 0.12 molar. So that ends up being about 0.006 for my concentration. So I'm going to take that away from my HA and add that to hydronium and my anion, leaving me with a very clear-cut concentration at the product side or the equilibrium phase. So we're going to have 0.11 for HA and then 0.006 for both hydronium and my anion. Now we're a hop and a skip away from being able to calculate my Ka. Notice though, I didn't include any numbers for water. That's because it's a pure liquid, so its activity is 1 and will remain unchanged throughout the entire problem. So next, we go right into Ka, product concentration over reactant concentration. So we'll find that that's 0.006 squared divided by 0.11. We can quickly solve, and that is 3.3 times 10 to the negative 4th. Let's try another problem. We need to calculate the Ka of this weak monoprotic acid, H, skull and crossbones. And we're given this, in this case, a little bit of a different piece of information. We're told that the initial concentration is 0.10 molar, but that its pH is measured to be 2.97. Now in these sorts of problems, the pH can only arise after having measured the hydronium ion concentration. And the only way that you're going to get hydronium ion is if you've reached equilibrium. So this is a very sneaky way of giving you the equilibrium concentration of hydronium ion. So let's set up what we know so far. Again, I always start with a dissociation equation so that I can set up my chart problem directly under that. I've layered in my initial concentrations already of 0.1 molar for my acid and zeros for my products. Now in this case, my change isn't necessarily given to me yet, and I'm also asked to calculate the Ka value. I can't not know both of those things. But remember, what I do know is that the pH at equilibrium is 2.97. So I'm going to do a little calculation with that number. What I will be able to find out from that is the hydronium ion concentration using the equation hydronium ion equals 10 to the negative pH. So if I plug and chug my pH in, I actually find that my hydronium ion concentration at equilibrium is 0.00107 molar. I'm going to fill that into my chart. And what that allows me to do then is, if I'm going from 0 to 0.00107 in hydronium ion, then my change must be 0.00107 molar. So then, according to stoichiometry, I would also have to have gained that much of my anion and lost that much of my HA, my acid. Now, notice with significant figures that there's essentially no change to the initial concentration of my acid, and that's actually a very important thing to note. because for some problems, based upon the K value that we calculate, we're going to be able to ignore that change to that initial concentration. More on that in a little bit. At this point now, we're a hop and a skip from finishing this problem up. So let's go ahead and plug and chug some of our other numbers in. So our K value is going to be defined as products divided by reactants. So that's 0.00107 squared divided by 0.1. And we find out that that equals 1.1 times 10 to the negative fifth. Now again, notice that K value, 1 times 10 to the negative fifth, and we were able to ignore the change to the initial concentration, something very important to remember, particularly as we start our next problem here. We are going to be asked to calculate the concentration of all of the species in a 0.15 molar acetic acid solution, and notice the K value. It's 1.8 times 10 to the negative fifth. Scientists have found that as a rule of thumb, when your exponent is 5 or greater on your K value, in other words, to the negative fifth, negative sixth, negative seventh, that your percent ionization, in other words, how much of your product is actually going to be made with respect to your initial concentrations, is going to be so low that according to significant figures, you do not need to subtract away anything from your initial concentration. You can just negate it. This also brings up a very important side calculation, kind of similar to what we would do with stoichiometry, like a percent yield. In these cases, it's actually called percent ionization. And what you're simply going to do is, for percent ionization, you're going to calculate either hydroxide or hydronium. I know it has the acid on here on the screen, but either hydroxide or hydronium ion concentration at equilibrium divided by your initial concentration. And the rule of thumb is essentially, if it's less than 5% ionized at equilibrium, you can ignore the change to the initial concentration. And what that correlates to, again, is a K value with an exponent of negative fifth or more. So now on to the problem. Let's again calculate the concentration of all of the species, in other words, all of the ions, in a 0.15 molar acetic acid solution, and we're provided with the K value. Now this is also an important thing to note. When they take the time to actually bother to tell you what the acid or what the base is in the problem, that is a very sneaky way of providing for you the K value. You should actually have a chart of known K values under standard conditions for most of these acids and bases. So again, when they tell you what it is, that should prompt you to go to the chart and to find the K value that goes along with it. First step of the problem, let's write out our hydrolysis equation. So for acetic acid, we have CH3CoO. I know that looks like a little bit of a different formula than you might be used to for acetic acid. And of course, that's reacted with water. And because this is defined as an acid, since it does have CoO inside of it, it is going to donate a hydrogen to the water to form hydronium. Simply write the leftovers right next to it with a -1 charge. So, time for our chart problem. So here you go, and we are going to start to layer in the information that we know, which would be the initial concentrations. So 0.15 for my acetic acid and 0 for my products. And because we are provided with the K value, that must mean that our change is going to be defined as X. And don't forget here, my K value is to the -5th. So what does that mean? I can ignore the change to the initial concentration. So I'm going to layer in a -0 for that column. That's going to simplify our math tremendously. Goodbye, quadratic formula. Both X's, though, for my products, and at equilibrium, very easily defined. We're ready to begin our K calculation. So Ka in this case does equal 1.8 times 10 to the -5th, and that's again always products divided by reactants. So x squared divided by 0.15. We go ahead, we quickly solve for our x value, and we find that it is equal to 0.0016. Now do be very, very careful. This is kind of a typical pitfall of most AP type problems, in that Most students are going to stop right now thinking that that's the solution to the problem. But the AP graders are going to be looking for you to define all of the concentrations of everything that is inside of the solution. Now that means you both have reactant and product still floating around in the solution. So do yourself a favor, after every single one of these problems, make a second little table of all of the concentrations present there. Kind of something that looks like this. So our acetic acid concentration remains unchanged at 0.15 molar, but our acetate and our hydronium ion are equal to each other at 0.0016 molar. Let's take a look at some bases. Bases are kind of interesting. How about we calculate the concentration of everything inside of a 0.15 molar ammonia solution, and let's throw in percent ionization just for fun. Now, weak bases, again, weak bases specifically, also need to have water as part of the hydrolysis equation. It requires it because otherwise there's no source of hydroxide ion. So here's our equation with ammonia plus water. The lone pair of electrons on that nitrogen is going to be able to kind of snag one of the hydrogens off of the water, creating ammonium and hydroxide ion. It's with this equation that we're going to layer it into a box problem. And again, we're going to start with things that we know, initial concentrations. And at this point, most people might not be able to go much further with the problem. So now remember that the author of this problem took the time, instead of giving you a generic weak base, they actually took the time to tell you that this is NH3, this is ammonia. So that should prompt you to go to that table of Kb values and look up what the value of Kb is for ammonia. And luckily for this problem, that actually equals the same as acetic acid, which would be 1.8 times 10 to the negative fifth. And now we're off and rolling. Since we're given our K value now, our change must be equal to X. And again, because we are at negative fifth, we can ignore the change to the initial concentration. Anything that's not 0, you can actually ignore the change to the initial concentration. So I layer in a minus 0 for my ammonia, but X's for my ammonium and my hydroxide. Now my equilibrium concentrations are defined, so I need to plug and chug that into a K calculation. Products divided by reactants, so that would equal X squared divided by 0.15. We solve for X. X is going to equal 0.0016. Again, before you're done, you're going to want to make a chart of the actual concentrations at equilibrium. So define the concentration of ammonia at 0.15 molar, and ammonium and hydroxide will equal each other at 0.0016. Almost done. Just one additional little add-on to the problem, and that's to calculate the percent ionization. In this case, again, you're going to want one of the ions on the product side, usually hydroxide, divided by your initial concentration of your weak base. So that's going to equal 0.0016 divided by 0.15, and in this case, with two significant figures, your final percent ionization is about 1.1%.